Okay, so second half, we're going to deal with conservative forces and central forces, and a couple of examples of non-conservative forces as well, since it's useful to know what all these terms mean as you go through physics. And in a lot of cases, people use them and they assume that you've already been taught them before, and it's very easy to find that you just haven't. So I remember when I came in to start teaching this subject, I had to remind myself what a conservative force was and what a central force was, and realize that I'd never really had these things described to me, and just work them out as you go along. Okay, so I want to define them properly here and set this up and get it stuck in your heads as you go further on through the subject. So a conservative force has two requirements to it, right? A force F is conservative if it only depends on the particle's position. So it doesn't depend on, for example, position and velocity, or velocity on its own, or time, or whatever. Okay, so you can think about this as like if you have all the possible forces that you can generate, there's some subset of those forces that will be conservative forces, and those are the ones that only depend on position and not other things, which is all this zoo of other forces that you have around that. Okay. And we do this quite a lot in physics. Some problems are more easy to solve than others, and also sometimes more useful. And we tend to create little classes out of those, and we know that we can use a particular approach for all the problems in that class, but all the problems that are outside that class, we have to use more advanced techniques for, right? And this is definitely one of those cases. Conservative forces tend to be quite easy to handle. We deal with them a lot in physics undergraduate courses. And then conservative forces are a bit more difficult. Sometimes you have to use some rather special techniques for them. And there's whole other forces out there that are even more complicated. You have to do more complicated things for. Okay, so that's the first one. The second point is that for any 2 points, 1 and 2, the work done by F is the same for all paths joining 1 and 2. Okay? And some of the reason why I wanted to be up here on Fuji today is that it's a really good example of conservative forces and non-conservative forces when you think about what the ideal case is. Okay? So if you think about ideal situations in physics, if I'm going to climb here from 7th station up to summit of Fuji, I'm going to be going through a change of height, right? And as you know from your first year courses, that change in height is corresponds to a change in potential energy, and that change in potential energy is mgh, so it's only height dependent, right? And so in going from here to the summit, I should do the same amount of work to overcome that potential energy to get up there. And it doesn't really matter which way, or it shouldn't really matter which way I go up, right? So for example, I can follow this nice trail behind me that snakes its way up Fuji, or I can just be a maniac and just charge straight up the hill, okay? And if you think about this in a completely ideal world where you take out all of the other things in the problem, that would exactly be the case, right? The amount of work that you have to do to go straight up Fuji is exactly the same amount of work you have to do to snake your way up this trail, okay? In a lot of cases, forces are non-conservative, and to give you an example of non-conservative force here, those of you who have been up Fuji will possibly recognize that I'm on the Gotemba trail, which we took for longer story reasons. And the interesting thing about Gotemba trail is that it's almost entirely gravel. So every step that you take up this trail is with the intention of 100% up, and the reality being about 50% up and 50% pushing gravel back down Mount Fuji. And so that means that the amount of work you have to do to go up that hill is more than just the gravitational potential energy change, but it also means that staying on very flat paths makes your life a lot easier than staying on very steep paths, because your ability to push gravel back down Mount Fuji increases as you increase the slope of the mountain, right? And so non-conservative forces, you end up being path dependent about which way you go through the system, in order to go from point A to point B, right? So if you really did climb up Fuji, up Gotemba Trail, you'll be exhausted coming up the path, and you'll probably just not make it if you decide to go screaming straight up the mountain. The nice fun part of it is that the fastest way to go down Fuji, which is why one of the reasons why I recommend Gotemba Trail, is that because it's gravel all the way down, you can just run literally straight down the mountain. You almost get into this sort of skiing type motion, but without skis. And going up to the summit takes something like most of the day on the way up to here at 7th Station, and then another couple of hours in the morning to go up. And you can go from the summit back down to 5th Station, which is the base, inside 2 hours, running basically down this giant gravel hill down the side of the mountain. It's so much fun. So if you ever come and climb Fuji, definitely come down by Gotemba Trail. It's the most fun you will ever have. Okay, so conservative forces. Force depends only on position, and it doesn't depend on which path you take from point 1 to point 2. And there's an interesting side point to the second one, which often doesn't get pointed out, but I will point it out because it's very useful when you do more advanced problems, particularly when you get into electromagnetism, which is that the fact that the work done doesn't depend on the path relies on the fact that the curl of the force is equal to 0. Okay, it's something I might come back and derive properly later in the mechanics course if I have the time to do it. But the way I always used to remember it as an undergraduate is that conservative forces are always forces that aren't curly, in that the curl is equal to 0. Okay, another one of these mnemonics that I like to have. Okay, so for a conservative force, we can define a corresponding potential energy in a meaningful way. And we can define that potential energy, U of R, just here, as the minus sign of the work in going from point 1 to point 2. Okay, and if we use the expression that we just generated on the last slide for relating work to forces, what this is minus the integral of the force with respect to position in going from point 1 to point 2. Okay, and so what we find if we do this as a derivative, so we can take the derivative of u, we can take the derivative of this integral of the force, and of course the derivative of u, if we present it as a 3D derivative, will just be del u. And the derivative of an integral is just the term itself, so we get our force back. And so we have something that looks like this. Force is equal to minus del u. And of course, if we take this out of our 3D coordinate system and just treat it as x, what this really means is that F is equal to minus du on dx. Okay? All right, so with that in place, I want to play around a little bit with the maths of conservative forces and just build up some pictures here. And those of you who've done second year quantum mechanics will see this kind of fit right up against the edge of what you learn about in your second year quantum mechanics courses. Okay? So we're going to define potential energy here as minus del u. And this is really just a 3D derivative of potential energy, right? This is like taking d on dx in a 1D system and saying, what's my equivalent of d on dx in my 1D system? It's this thing that we call del, okay? Just to keep the notation kind of tight. All right. So we can convert this into 1D to keep this nice and simple. And most of the time in this mechanics course, we will actually use it in its 1D form. Okay, so some of the reason why I've put the 3D derivative form in here is just to connect ideas together for later parts of your degree. So what we would have here is f of x is equal to minus du on dx. And of course, some of you will have seen this before in books written as dv on dx, because some people like to use v for potential energy, some people like to use u for potential energy, and I like to swap between the two depending on what the context is, and I'll do that in the course. It's the one thing that's hardest to avoid is swapping between those two labels for that sometimes. Okay, so what we can do here is pull the dx over. So f of x dx is equal to minus du. And we can integrate both sides. So this will give us, and again, we have to choose positions to go through to. So we might call them 1, 2, we might call them A, B, we might call them X naught and X. Again, this is one of these things in physics. Different people use different notations in different places, and you kind of just got to get used to the fact that it sort of means the same thing. So here is X naught and X. Okay, and the reason why I'm using X naught and X is so I can tie back to my earlier slides in the lecture, even though I might be talking about point 1 and point 2, or 7th station in the summit, which would be X naught and X, or Z naught and Z, if we want to be serious about our coordinate systems. Okay, so we've got f of x dx equals minus x naught du. Okay, so we're going to integrate both sides here. We put this on both of the two sides. We know from our work kinetic energy theorem, this first term on the left is really just t minus t naught, right? I'm not going to do that again because we've just derived that thing. And of course, if we integrate du, we're just going to get u. So this thing is going to be minus u x naught. And this thing would be then ux, let me do it properly, minus u of x minus u of x naught. And I could write this if I want to as u of x naught minus u of x, okay? All right. What we can do is take the two sides of this equation and shuffle them across, right? And again, this is one of these things we do quite a lot in physics and approach. Okay, so I'm going to call this one a shuffle for the moment. And what I mean by shuffle is I'm going to take one of the terms from the right and put it over on the left. I'm going to put one of the terms on the left and move it over to the right, because what I've got is I've got T and T and U, which is nice for the moment. But what I've also got is a quantity connected to X and a quantity connected to X and a quantity connected to X naught and a quantity connected to X naught. And if I shuffle this across, now I've got all my X related terms on one side and all my X naught related terms on the other side. And that might get me to somewhere useful, okay? So this thing would be T plus, let's just call it U now. And this will be equal to, I'm going to put the T naught on the other side, and I'm going to call U at X naught U naught. Okay, so U naught and plus T naught over here. Okay? And this thing can be equal to, we know it's not 0 most of the time, but we know we can set it equal to some constant, right? And we can call this thing E the total energy, right? We know physically what this thing is. We take the kinetic energy, we add a potential energy to it, and then we go to some other position, and we're being completely arbitrary about our two positions, right? So we know this thing is always going to hold. That the kinetic energy at some position plus the potential energy at some position is going to be equal to the kinetic energy at some position plus the potential energy at some position. Call this thing a total energy, and we have this thing being a constant all the way through the system, right? It's just a logical thing. And so what we just arrived at from simply a definition of potential energy and our work kinetic energy theorem essentially is that for conservative forces, the total energy is conserved, okay? So you can imagine that if I'm going from 7th station here up to the summit, and I should be able to take the amount of energy required to get up there, and then in coming back down get all of that energy back again. And in a conservative system, that would be true. But in the reality here, this is actually a non-conservative system, and so what would happen is I have to bleed some energy to get up there, and then I don't get all of that energy back coming back down again. Okay. So the nice thing about conservative systems is that the total energy is conserved, and as soon as you have a non-conservative system, that total energy is no longer conserved. Okay. And now you can see where the name conservative and non-conservative comes from. Conservative forces conserve the total energy. Non-conservative forces don't conserve the total energy. You're losing energy out of your system to somewhere, and usually that is either just waste energy, heat, that sort of thing, or a lot of times in thermodynamics you're losing it to entropy and processes like that. Okay. Okay. So what we get in here is a thing we call the energy equation. And it basically is that E is equal to T plus U. Okay? And sometimes we'll call it T plus V as well, depends which way you're looking at. Okay? And let's just play around with this thing for a minute and have a look, because there's one interesting place that this can go that we can think about. So this is a half mv squared plus u of x. And let's pull the terms out and try to get this thing in terms of velocity so that we have some simple expression for velocity. So we would pull our half mv squared out the front, drag the u of x over, so this will be e minus u of x. We can carry the half m back over the other side, so this will be v squared is equal to 2 over m e minus u of x. Take the square root of this thing, so v is equal to plus or minus the square root of 2 over m e minus u. So, and there's one really obvious solution that comes out of this thing, which is that if E is equal to U, in other words, all of the energy is potential energy, then V is going to be equal to 0 and our particle is going to be stationary, right? So what we've basically done is all our total energy is potential energy, the kinetic energy component is 0, the velocity is going to be 0. Okay, that's one really obvious solution to this thing. What's nice here is that we can plot this thing as a graph. And so what we can do in here is, oops, let me try and draw straight lines here. A little bit sloppy. That's a bit better. Grid paper's there for a reason. It's nice. We can plot our total energy E on this axis. Actually, we're not going to plot our total energy. We're just going to plot energy as a quantity, whatever it is. Okay, so let's specify this as just any energy, just to be really clear on what it is that we're plotting. Here's our position x, and what we would have here is our total energy for the system, and we can draw a line across corresponding to this because, of course, it's conserved, so it's a constant quantity. And then what we could do is plot our potential energy as a function of x. And I'm not going to plot anything completely meaningful here. I'm just going to plot some random curve of what potential energy looks like as a function of x, right? So you can imagine, maybe it does this and does something like this, for example. Okay, so this is our u of x, just here, right? What you'll notice is that there's crossing points in this thing, so we can delineate these if we want. So there's one just here, there's one just here, there's another one just there, and another one just there. And what we've got in here is we've got places where the potential energy for the system would be greater than the total energy, right? And obviously this equation we've got up above for our velocity has the square root of E minus U. And so if U is bigger than E, then this term up in here, E minus U, is going to be less than 0. And if it's less than 0, we're going to get an imaginary velocity, right? An imaginary velocity doesn't really have any meaning to us other than that you can't really define motion in those places, right? So these regions here are basically places where, at least as far as classical mechanics is concerned, you just don't have motion at all, okay? And then in these regions here, U is less than E. And of course, if we think about our E minus U now, E minus U is positive. When we take the square root, we got a positive quantity, we're going to get a velocity, okay? And that means our kinetic energy would be finite, so we could plot, if we wanted to, on this graph kinetic energy. I won't do it because it'll clutter up the graph, but you could do it if you want. And so what you have in here is essentially classically allowed motion, where V is greater than 0 and T is greater than 0 as well, okay? And so if you think about a particle that's sitting at this particular position, it has now a kinetic energy, and of course there's a plus or minus on our square root up there, so it could be going this way, it could be going that way. And what happens as it moves along this system is that it goes, you know, it starts to slow down, and you can see that because its potential energy is increasing, and the kinetic energy is E minus U, so that it'll be getting less and less and less. And then when it gets to this point here, it will stop. And when it gets to that point and stops, there's then a force, which is minus du on dx. And you can see du on dx here has a slope that points back that way, so there'll be a force acting back in that direction. So that particle will head back in that other direction, right? And so then it will go up this other side and do the same thing, stop at the top. And so what you've got here is essentially just oscillatory motion between the 2 points, okay? The nice reason to point this out is because if you think about this, you'll have seen exactly the same kinds of graphs in quantum mechanics courses, right? And what happens in here is that these positions here are essentially the places where you get wave-like motion of your particle. And then out here into these classically non-allowed regions where the potential energy is greater than the total energy is where you get your sort of evanescent solutions that allow you to do tunneling problems. Okay, so there's a parallel between your classical mechanics and your quantum mechanics courses that, for timetabling reasons, mean that you do quantum mechanics before you do classical mechanics, but sometimes it's nice to do them the other way around because you start to carry the concepts out of your classical mechanics course into your quantum mechanics course, and they colour the way that you think about quantum mechanics a little bit. Okay, so it's really nice sometimes to, again, try and stitch these subjects together from different sides. Okay, so that's conservative forces. Central forces, I'm going to point to very quickly. I don't want to get too deep into them. I just want to make sure we're completely on the same page about what is conservative force and what is a central force. Because you'll sometimes see the two terms, and I've seen lots of cases where people just, who are new to the subject, get confused about the difference between the two, okay? So a force is central if everywhere it's directed towards or away from a force center, which we take to be the origin, okay? So you can essentially see central forces as a subset of your conservative forces where you have a central point and your force is directed radially from that central point, either outwards or inwards in that system. Okay, so the classic examples of central forces are gravity and the Coulomb force. An example of a conservative force that's not a central force would be essentially, I guess, gravity in the Mount Fuji context, where it really just does point up, down as a linear force. and there's no center to it. Now, we all know, of course, that if you look far enough out on the Earth, it's not flat, it's spherical, and so the force appears to point upwards at every point on the Earth, but actually it's a radial force. Okay, so it's not the best example in the world, but another example would be, say, a spring is definitely not a central force. Okay, there's no center component that you can work radially around, but even that's an artificial example because you may have a constraint in the system that makes that a little funny. Okay, so I kind of pointed to central forces being a subset of conservative forces, which is true, but that subset of central forces is not wholly contained within the subset of conservative forces. Okay, so if we go back to me pointing it out in my screen, got all the forces, you've got conservative forces in this little corner, and you've got central forces inside that, but that central forces can actually extend outside that space into the non-conservative forces as well. Okay, so you can have conservative forces that are central, and we deal with a lot of those in physics. You can have central forces that are non-conservative, and those end up being often rather complicated cases. But one nice thing about this little bunch of central forces that it sit inside the conservative forces is that those central forces are spherically symmetric. Okay, so they end up being really nice to deal with. And again, this comes back to this idea of curl being equal to zero or non-equal to zero in these particular cases. Okay, we might come back to that if we to central forces in more detail if we need them later in the course. Okay, so I just want to finish off by dealing with an example problem because I don't want the lectures to end up all being derivations and no examples. And so I'm going to do an example of just handling a mechanics problem in a Newtonian way, but use non-conservative force of drag as my example so I can sort of kill two birds with one stone, so to speak. So a really good example of non-conservative force is drag. It's a force that's not a function of position, it's a function of velocity. And so if you think about a stationary object, there's no drag force. And then as it starts to move through a fluid like the air, there's a force that results from having to push air out of the way to move forward. And the faster you move, the more air you have to push per period of time. So if you've got a slow velocity, then the amount of air you have to push to move forward that far is less than if you have to have a high velocity, you have to move that far in the same amount of time. So you've got a force that scales with velocity, and it's a non-conservative force, obviously because it doesn't depend on position, but also that that drag force ultimately leads to total energy not being a conserved quantity. So let's go through and do some maths for this because this is really where I want to focus. We've got some body, and let's call the velocity going downwards because you don't expect to jump out of a plane and go upwards, you expect to go down. And we're kind of led by the force that first kicks off this whole problem. So there's a force due to gravity pointing downwards that's equal to mg, and this object has a mass m. And then the fact that you're falling under gravity means you have velocity, and then there will in turn become a drag force, Fd, that's equal to b Vy in this case. And we could write f as all sorts of functions of y if we want to, and quite complicated ones to model drag really, really well. But here we're going to take the simplest case, which is just that f is linear in velocity and put a constant of proportionality, which we'll call b. Okay, this is a really common approach to just getting simple answers to problems. And sometimes they're not enough, so you have to do more complicated problems. So if we're dealing with a Newtonian mechanics problem, there's a set of steps. Okay, usually the first is we want to start with an equation of motion that's the sum of the forces, right? So we have our equation of motion. And it's really just the total force is equal to the gravitational force plus the drag force. And this is a vector equation at the moment that I'll basically treat as a scalar equation and put direction back in later. And I can do that really easily because the only direction that's relevant is up, down. Okay, so this thing would be, considering down direction to be positive, led by the dominant force, which is gravity here, we have mg minus bv. Okay, so the next step here is basically to look for useful parameters that come out from balancing forces. And this is one of those problems where forces will ultimately balance, right? If you think about this, you've got an object that falls out of the plane. Under gravity, it goes faster and faster. Eventually, that force due to velocity gets bigger and bigger and bigger. Eventually, that force due to drag becomes equal to the force due to gravity, and they cancel each other out, and you reach a constant velocity. And that's an interesting variable called the terminal velocity. Okay, so we can come in here and write terminal velocity Vt, let's call it, and it's the case where the force due to gravity is equal to the force due to drag, okay? And we can write this as mg equals bvt, and isolate vt, so this is mg on b, okay? So this is ultimately what our terminal velocity is. It's a combination of mass, gravitational constant, and B, which is essentially a coefficient of air resistance, which is basically made up of two things. One is the density of the air. If the air is really thick, your terminal velocity is low. If the air is really thin, then your terminal velocity is high. And another one is like a aerodynamic profile, right? So anyone who's jumped out of a plane will know if you lay flat, you have a lower terminal velocity than if you point down this way, because you hit terminal velocity falling flat. And if you suddenly go like this, your drag is reduced. Gravity once again dominates, so you speed up until you reach a new equilibrium between your gravitational force and your drag force. Okay, and then you might be doing this and go like that, slow down. Good example of inertial reference frames there. Okay, so we can get that, but often in mechanics, what we're really interested in is the dynamics, and that usually comes about by then using an additional thing, which is Newton's second law. Okay, I'm going to break my own rule and write it as F equals ma at first, but then I'm actually going to define it like this: Vy dot, because that's ultimately what it is, time derivative velocity. And this thing will be equal to mg minus bv, using the expression we had up above from our balance of forces, okay? And we've got a problem at the moment, which is there's too many variables. There's an m, there's a g, there's a b, there's a v. It's going to be really hard to deal with. Let's just put a y in here. And one way we can deal with this is basically by cancelling out our g using the expression for terminal velocity. So we can write this as g equals bvt on m, and substitute that into our expression. So this will be m bvt on m minus bvy. The m's cancel, and we can isolate the b. So this is bvt minus vy. And often what we want to do is actually bring the variables to the front and the constants to the back, right? So we can write this as minus bvy minus vt. And you don't have to do that, but some people like it better that way. It's a bit more convenient to handle, okay? The last step we can do here is isolate v dot. So what we've got here is an expression v dot y is equal to minus b on m vy minus vt, like so, okay? What we've got here is an ordinary differential equation, right? And once you get into second year mechanics, we hit up against these again and again and again and again, and we're not going to be shy about naming them as such things, and even classifying them in various ways so that we can solve them, okay? It's a good reason why you do differential equations courses in a really well-designed physics undergraduate degree, in a mathematics course, and the mathematicians are probably going to want to kill me for saying this, but the two big lessons I took away from my differential equations course, and I learned lots of stuff, it was very interesting. The two big things that I learned were the best approach is to try and guess the solution and then prove that that's the solution. And if that's not the case, then you should look up somebody else's solution to the problem when they've solved it previously and try to use that as your guess and go from there, okay? And in a sense, you can imagine this a little bit to be like physicists outsourcing to mathematicians. Mathematicians solve a whole pile of ordinary differential equations because they're interested in ordinary differential equations. And then we're interested in solving problems. Sometimes they turn up a differential equation, and then we just go and take a stock solution off the shelf, bolt that into the problem, make it fit, and keep going from there. Okay, so it's useful to know that these things exist, but you don't need to know how to solve every DE in the world, because ultimately, a lot of the times in physics, it's the same type of DE coming up again and again. You kind of know how to guess solutions. Okay, so the first step in doing this actually is not to solve that DE, but to make a little substitution, because it makes our lives a little easier. And the substitution we're going to make here is that U is equal to Vy minus Vt, because it's going to guide us to our solution. And this is a really common approach you learn in differential equations courses. Of course, we're going to need U dot. U dot will be Vy dot minus Vt dot. And of course, Vt is a constant, so Vt dot is 0. So this thing is just Vy. Okay, Vy dot. And so we can rewrite our differential equation. Let's call it 1. We can rewrite that thing as U dot equals minus B on mu. And let's call this one 2. This is a really obvious differential equation, right? Everyone knows this. You see this in first year. The solution to this thing is just an exponential. And because the derivative out the front is with respect to time, it's an exponential in time, right? So we can kind of write ourselves a guess solution in here. And that guess solution is U equals A E minus BT on M, which we can also simplify if we want to AE minus T on tau, where tau is equal to M on B. Okay, and this is a really common thing to do, substitute that tau on the end and have a T on tau minus T on tau. This equation turns up quite a lot in physics, and in a lot of cases we have that tau and we call it a half-life in nuclear physics or some other thing in other places, okay? Really common way to write it. So what we've got here is we can now back substitute our U, okay? So this would really be Vy minus Vt equals AE minus BT on M. And this A in here at the moment is a free parameter. It's one of those things when you solve DEs, you realize that you need to put some free parameters in so that it can adapt to various states of the problem. And it's one of those things, it's hard to give a good guide of how to do this. I could add a constant, I could do some other things in here. You kind of get guided after a while by doing lots of problems to know what you need for the right situation, which is why as an undergraduate physics student, you should be spending lots of time doing problems. It just sort of teaches you how to do these things. Anyway, we're going to introduce one. It's A. It's enough to solve the problem, just based on experience. And so, as you know, the next step usually in dealing with these things is to resolve the free parameters with boundary conditions. And in this case, there's one obvious boundary condition, which is time equals 0. Okay, so when time is 0, we know that Vy will be a starting velocity. Let's call it Vy 0. And later on, I'm going to assume it's 0, okay? So let's call it 0 for now, but let's keep it in just so that we get proper equations coming out of this thing. Okay, and we also know that our E minus T on tau is going to be 1, because E of 0 is 1. And so what we can do here is lock down A. Vy minus Vta is equal to A times 1, which is just A. Okay, so we know that A is Vy minus Vt. Fairly simple, we've just locked down our free parameter in that equation. We've got one more step here, which is that at the moment, we still have our problem in terms of U. So if we recast our solution again, our solution is actually U equals Vy minus Vt E minus T on tau. And I'm going to keep using tau because I like it. It saves me things that I have to write on the page. We need to go and take that back from being a problem in U to being a problem in V, right? And you'll remember we have this expression up here, U is equal to Vy minus Vt. It's how we defined U. And so U U is, let me go back and remind myself, Vy minus Vt, Vy minus Vt. And what we have here is that Vy is U plus Vt, okay? So now we can get back our final solution here, Vy as a function of t, which will be Vt, let's pull that out the front, plus U. So plus Vy minus Vt E minus T on tau. All right. And then, actually, this would be Y naught. Can you this back here? This would be Y naught. Let me see. This would be Y naught there. That would be Y naught there. That would be Y naught there. That's Y. That's Y. And that's Y naught. Okay. So just highlighting a really good thing that in lectures we don't make it obvious enough because we like to stand up and show that we know all the way through and we get it right all the way. That's not the reality when you're a student. It's not the reality when you're a lecturer, actually. Sometimes you'll notice all the way through this course I'm going to go back and clean up little bits and pieces. And you should get in the habit of doing that as part of your problems, going back and saying, hang on, have I skipped something? What's going on? You need to keep processing the maths in your head while you're dealing with your problem. And then you spot little problems like that as they come. Okay, so what we're now going to do is take Vy naught equals naught, just to make the problem simple, right? When I jump out of the plane is sort of doesn't have any upward downwards motion. I can just come out of t and I can get a simpler solution, right? So we're going to take Vy naught equals 0 now. And that will mean that Vy of t is V of t plus V of t E minus t on tau. And we can collect up our Vt up front, Vt 1 plus E minus T on tau, like so. Okay, let's do a quick reality check. There's two limits here. First limit is time equals 0. When time is 0, E minus T on tau will be 1, right? Actually, I've made a mistake. Let me pursue it because it's actually useful. T equals 0. E minus T on tau is 0, and I would have 1. 1 plus 1 is 2. That's not right? I smell something wrong in here. So what's gone wrong? Up here where I've made my Vy naught 0, let me just change the red pen so I can highlight it. Up here where I've made my Vy naught 0, I've got a minus Vt, and I haven't carried the sign here properly. So this thing here is actually a minus. This thing here is actually a minus, right? So now let's go through and check that we've got this right. Time equals 0. E minus t tau is 1. 1 minus 1 is 0. And so our velocity is 0. It's exactly what we'd expect. It's our initial condition. And then the other limit we can take in here is to take t goes to infinity. And if t goes to infinity, then E minus infinity is essentially 0. 1 minus 0 is 1. And so we get Vt. We get Vt coming out. And that's exactly what we should expect, right? We should get towards our terminal velocity. And so we can take this expression that we've got up here and we can plot it. And what we get if we draw straight lines as our axes, it's a bit straighter, like so, is Vy on this axis, t on this axis. Here would be our terminal velocity Vt. We can draw a dotted line across here. And we'll start at 0, and we get an exponential increase up into that terminal velocity like so. And there would be characteristic times in here, tau, 2 tau, 3 tau, and so forth. You can calculate those out based on the exponential, okay? So this might be a problem that you might do of, person jumps out of a plane, work out what the terminal velocity is, and then draw a graph of velocity as a function of time and how long do you have to wait until you get to 95% of terminal velocity, for example. Would be this as either a tutorial problem or assignment problem or exam problem, doesn't matter what it is, that would be the kind of problem that you would be setting out to solve here, okay? Really nice little example of how to deal with these sorts of problems. And then just before I finish off, one last point, and I really don't want to get into it very deeply. So I've put some maths in my notes just so that everyone's seen it before, but we're not going to do impulse problems too much, mostly because a lot of them are very, very hard to do. But sometimes forces occur in a fixed position as a function of time, and those are also non-conservative forces. And collisions are a really good example. So what you would have is two objects coming in towards each other. the force is actually at a fixed position. So it's actually not position dependent, or at least, in a proper collision. Some collisions you might push across and you might have a position dependent part to it. And this is why these problems can be really complicated to solve. But there's a time dependence to this thing. So these two bodies come together. And then there's a force that depends on time that really results in materials properties of the two objects, right? So you can imagine as these come together and have to change their velocity, you're kind of pushing it on this object and then it pushes the other thing back out, and same with my Apple Pen. And so you've got a force as a function of time, but not necessarily as a function of position or even velocity, right? And in a lot of these problems, you're really worried about a thing called impulse. And impulse is basically the change in momentum imparted in a body, and you can obtain it for these types of problems as an integral of force with respect to time. Okay, I think I'll leave it there because it's at this point it's not an important point of the rest of the course. And if we use it a little bit later in my part, I'll come back and address it a little bit more detail. But for the moment, I think I just wanted to point out it's another example of a non-conservative force. And so we'll leave up here for today. And in the next lecture, we'll basically start doing something that's very, very new for you students, which is Lagrangian mechanics. See you next time.